Hello everybody. I hope that so far you have seen that in this room there is Mark with his large-scale application talk and not the real-life sharding talk which will happen in the other room, just to this side. Okay? Is everybody fine with that? Thank you. So, let's welcome Mark, which is a long-time Python and EuroPython supporter, and his talk on large-scale Python applications. Thank you.
Yes, welcome. Thank you very much for coming. I didn't really expect this many people to come to the talk. I hope I won't disappoint you. If you have questions, is it loud enough back there? No? Can I turn? Oh, okay. If you have questions, then just raise your hand and we might be able to then deal with it directly in the talk rather than afterwards, or you can just take notes and then just ask the questions afterwards. Right, so who am I? I'm Marc Lemburg. I've been with Python for quite some time. I'm a Python core developer. I am a member of the PSF, a board member. I have a company called Egenix. We're doing projects and consulting in the Python space, so we help other companies who have great ideas to implement those great ideas in very short time frames. And I live in Düsseldorf. I like beautiful things, and that's why I'm giving this talk here. So this is the agenda for the talk. I'm going to give a short introduction, then talk about application design. I'm probably going to skip the third part because I have too many slides for this for the time slot. But if there's interest, I can give a presentation tomorrow in the open space, and then we can have some time for discussion. So let's start with the introduction. I'm going to talk about designing Python applications. So the use case is a customer comes to you, has a great idea, and nothing much else. So you get, for example, told that you need to implement a trading system. Of course, the customer knows more or less what the trading system should do. It gives you some outlines, but then all the rest, how you actually implement it, how you structure your application, is pretty much left up to you. Now, Python makes it very easy to implement those complex applications. Unfortunately, it also makes it easy to create bad designs very, very quickly. On the positive side again, you can refactor Python code very easily. And that's something that's very important in application design, because in our experience, you normally don't get it right the first time. So if you're doing a project with a customer, the application design is the most important part in the whole project. If that goes wrong, your whole project will go wrong. You won't meet the deadlines. And so you have to pay very much attention to that, especially when working with Python, because the actual implementation process in Python usually doesn't take that long. The title of the talk includes large-scale applications. Now, what's a large-scale application? Of course, it's hard to define, so I just made up some numbers. And these numbers are based on the experience that others have with implementations for example, Java or C++. If you're doing Java or C++, the large-scale application has about 1 million lines of code. That's when you start talking about large-scale application. Now, Python code is usually much more efficient in expressing things that you want to do, so the numbers are much, much lower. So when I'm talking about large-scale application, I usually refer to applications that have at least 100,000 lines of Python code for server-side applications. For client-side applications, it's a bit smaller. Plus nowadays, because there's so many excellent Python libraries that you can use in your projects and your applications, you usually add about the same amount of code in third-party code to your project. So you have about 200,000 lines of code. How many of you have written applications of that size? Oh, quite a few. That's interesting. So you can tell me later on if I was right or if I'm wrong. Right, so why write applications in Python, large-scale applications? For many of you it's probably pretty straightforward. I mean, that's why you're here. Python is of course very efficient. You can have small teams write big applications. You can have small teams compete against big companies, and I'm talking about companies like IBM, like Oracle, who usually want to do everything in Java, and so they're slower and they cost more to implement the projects. You can be very competitive. So if you're a small shop, then you can easily compete against these bigger companies because they can't move that fast and are not that flexible. And if you're an investor, of course, it makes a lot of sense to implement your idea in Python because you don't have to invest much and you still gain a lot afterwards, as you can see with all the web startups that have been using Python in their application. It's very flexible. You can do rapid design, you can do refactoring. It's very easy to do rollout, so there's nothing much to do. You don't have to install complex systems. Python is usually already installed on your machines. You can very easily adapt it to different environments. Say you have a change in environment. Say someone wants to move from a Linux machine to a Windows machine or the other way around. It's very easy to do. There's no login. You don't have a situation like, for example, when you do a project with IBM, you always get WebSphere, and then you're logged into that particular application framework. It's very hard to move away and move to some other framework again. You don't have that with Python. Time to market is very important, especially nowadays, because the market is moving very, very quickly. So it's important to develop quickly and fast and be able to react to customer needs. If you enter the market with a new application where you're not sure what the customer actually wants, it's very important to look at the user feedback that you're getting. And you have to take that user feedback and then implement it into your application and improve it. So all these things make Python the perfect choice. That was the intro. Now for the application design. So what's a typical scenario? For a large-scale application, like the example I gave with the trading system, you usually have complex interactions between the different program parts. So basically writing down your home project in a specification would fill maybe 100 pages or so in terms of specification. So it's very complex to do. You have complex work concepts. For example, in a trading application, you have to think about how to manage the different things that you're working on. You have different I/O types, so you need to interface to various different backends, databases, text files. You get streams with data from the internet. You have to interface to Excel or MS Office or LibreOffice or Exchange. Yes, right. And you have to take all of these things into consideration. So the application will have to deal with a number of things. You have to have a user interface. You have to have an application interface because you need to define how the information flows through your application. Then you have to have business logic. You need to implement all the different interactions between the data objects that you have in your application, define certain constraints and implement those. Finally, you have to have a storage interface, obviously. You need to store the information somewhere. Now, there's the next slide. There it is. If you look at this is not a very uncommon kind of problem. And that's also how I came to this kind of structure that I'm showing you here. If you look at application design, it's actually very much like when you're structuring a company. So you have divisions, you have departments to set up, to separate the work. You have responsibilities that you need to define to make the company work internally, and you have processes to follow in the company. And I would like you to keep this idea in mind and in the back of your head when following the talk. So, what's the design concept that I'm using for large-scale application design? It's actually made up of two parts. One is a structural approach, and the other is going to come on the next slide. The structured approach I'm using is divide et impera. If you've studied computer science, you probably know that as divide and conquer. So you take a complex project, you divide it up into smaller pieces, solve the small pieces, and then put everything together again. And I'm going to show you that using a top-down method. This top-down method has, as you can see here, it has six items on it. This may be a bit boring for you, so I don't mind if you want to have a cup of coffee or just take a short nap or something. I'm going to summarize things afterwards. The other thing to keep in mind is, well, you can probably guess it from this import app. Oops, sorry. The Zen of application design. I just made this up. So the very basic things that you probably mostly know. One is keep things as simple as possible, but not simpler. That's the KISS principle. It's said that Einstein invented this. Then there's the DRY principle, so don't repeat yourself. I used the term before, doing things twice, think twice. Then the next one is probably, well, in the context of breaking things up into smaller pieces. If things get too complex, you just use decomposition, so you break it up into smaller pieces. And then if the breaking up of those parts into smaller pieces becomes unmanageable, well, of course you need management. And that's, again, very similar to what you do in a company. If you have departments and divisions, you keep splitting them up into smaller pieces, and then you add managers to those divisions to actually make things work. And then, of course, you have the employees working in those divisions to get small things done. Something else that's important is there's beauty in design. So if you write code or if you design something and it looks pretty ugly, then there's something wrong with it, and you can probably do better. Right, so I'm going to step through this top-down method of application design one by one. So let's start with the application model. What's an application model? An application model basically defines how you set up your whole application. So let's say you have a trading system again. You can do the trading system as GUI application that you install on a trader desk. And if you try that, you'll find out that in a bank it's very, very difficult to get an application installed on a trader desk. So you might think, well, it's not a good idea. I'll use something else. I use the stuff that's already on the trader desk and then just write an application that works like that. So I'm going to use a client-server application. So basically I have a server and use the web browser as my client machine. Or you have a different kind of setup. You need to do batch processing, for example. Then you would use a single process kind of setup. And the data just flows through your application, so you have a pipeline approach. And there are many other different kinds of application models that you can choose. This is usually something that you have to decide up front, depending on what the needs are for your project. In some cases there are external requirements, like this trader desk example, that you have to meet. So it's very important to get this right from the start. Next thing is the processing model. So processing model just means, well, how are you going to set up your application in terms of processes. So you have a single process approach, you have multiple processes, you have multiple threads. Like in a GUI application, you typically have multiple threads. Or you have asynchronous processing, where you kick off some task, you put it into a queue somewhere, you have some worker processes working on it, and then after all the processing is done, you pick up the results again and then put them into some report and show that to the user. Plus, of course, you can mix all of this. So how can you decide on which processing model is best? Well, you have to ask yourself a few questions. One question is, you need to, of course, in the application you need to share data. So you need to make sure that all the data is very close or very central to the components using that data. The other question is where state is kept. This is not necessarily the same. So you can have data, like static data, for example, of stock prices that you can keep in in a database, and that data won't change because it's, well, once you have the stock prices, they won't change anymore. Whereas state is something that usually depends on the user interaction with the system. So you need to make sure that the state is kept in that place where you actually need it. And you also need to make sure that state doesn't leak into areas where it shouldn't be. I'm going to talk about that later on a bit more. And then of course you need to define what an application instance is. Application instance basically means that you take your whole application and you can instantiate it multiple times. This may sometimes be necessary, may sometimes not be necessary. For a GUI application, for example, you just have one instance, but for other applications you might have multiple instances. Okay, so now we're going to break down by functionality. So we already know the application model, we know the processing model, and now we need to look at the application and see how the data should flow through that application. So what you typically have is you have layers in your application. So the data comes in at the top, you have an interface logic, you have a server logic, application logic, storage logic. That's the typical kind of setup that you have in an application. And so the data comes in from the top, goes down in the storage logic, and then you do some, I don't know, query or whatever, and then you send it back up again. So that's the kind of separation that you can do. That's the first kind of separation that you can do, and decomposition that you can do with the application. So you have a top layer, interface to the outside world, you have the intermediate layer, which basically then defines the business logic, and you have the bottom layer for doing stuff like data storage. These are a few examples of such layers. For client applications, you have a GUI, you have the business logic and the storage logic, so it's very simple. Web applications, you all know, I don't have to address that. For batch processing, you do I/O, and you need to, of course, attach the business logic and storage logic for that. Plus you can have custom models depending on your needs. So let's look at the web application, because that's something that we probably all know. You have a situation where the client is a standard web browser, you want to do some AJAX. You have a server, takes lots of load, has to do lots of calculations, has to be fail-safe, needs to scale, is connected to a database, nothing special there. So how do you do this? You first decide on the application model. Well, obviously it's a client-server application. The next thing is processing model. You want it to be very stable, very scalable, so you use multiple processes for that, especially because of the Python GIL. You want to make sure that all your cores are actually used in your server. And then you have the standard layer model for your server processes. Okay, so now you have your layers. That was easy. But if you actually try to implement all those layers at once, you'll find that it's very complicated to do. For example, if someone tells you, well, please implement the whole business logic needed for a trading system, that's something that's too complex to do in one go. So again, you may need to break up things. And what we usually do is we break up those layers into components. So what's a component? You have the layers. They are basically data driven. So the separation is given by the way that information flows through your system. And you have the complexity is too high in those layers, so you need to decompose those. Now what's very important with the components is that you loosely couple them. So you don't have direct interaction between the inner parts of the components, but you always go through an outer layer. The components themselves, they usually implement high-level concepts in your application. So say, for example, you have a user component that takes care of user management, or you have a log component that takes care of logging things, or you have a database component that takes care of interfacing to the database. And the components need to be independent of each other. I'm saying this because I'm again thinking about the refactoring that you have to use, that you often have to do afterwards, and the changes that you often have in projects when implementing the solution. you often find that the customer then changes his mind and then just wants something else, wants a different database backend, for example, or wants a different kind of authentication mechanism. Then you have to replace that. And in order to make that easy, you need to make sure that your components are written in a way that they are independent enough of each other so that you don't have to rewrite everything. So these are a few examples of components. Like I already mentioned, you have a database interface, user management, session management, caching, lots of others. And as I said, they need to be easily replaceable. And if you get that right, you can even change the processing model afterwards. So refactoring goes a long way in that case. Changing the processing model means, for example, you go from a multi-threaded application to a multi-process application. Right, loose coupling I already mentioned, so I'm going to skip this. So how does the implementation actually look? What we usually do is we just put the whole component into an object. So we define a class, we have a single object implementing that component, and then the component provides all the facilities. It provides an API, and the API is then used for loose coupling. So whenever you want something from that component, you only use the API. You never go directly into the component. And that's very important to do. The other thing to do is to not keep state in those components. So you can take the object and use it for multiple things without having to worry about the component changing internal state. Okay, if you put all this together, you get something like this. You have a process boundary, you have an interface layer, server layer, application layer, storage layer, you have components within those layers, and next to all this you have an application instance layer. And the application instance layer then provides facilities that are used by all the different other layers. Like, for example, an error component which takes care of the error reporting. For example, you could put a Sentry interface in there. Or you have a log component where you keep your log files, or you put the logs into a database. And then for debugging, you usually also have another component. There's one component that's special. This is something that we found is very useful to have. We call it a system component. And that system component is an object which basically hooks up everything. So what you do is, if you want to create your application instance, you instantiate that system component object once. And that system component object then instantiates all other component objects that you have in your system and references them. And so if you want to access any part of the system, you can always go through the system object to access those. And even though that creates circular references sometimes, it makes things very easy. If you have a large application, you can very easily then maintain the loose coupling in your application. Right, so this is basically how applications look in that design. Next step. So you have the components, but the components may still be too complex. Like I said before, if you have divisions in your company, and the divisions are still too well. If you just put employees into a division, they need to do something in a coordinated way. So you need some management to go with it. So what we have is management objects. This would be something like, for example, if you have a database component, a management object for that database component could be an interface to a particular database. Or for the log component, could be an interface to a log file, or could be an interface to Sentry. So the management objects, they help simplify the component objects some more. Because what you want to have is you want to have small objects. So the component objects should be small as well. So in order to do that, you just give them some helpers, and those are the management objects. Now, how do you decide whether you want a management object or a component? Well, that's hard to say. I mean, you can basically say that you have the component objects doing the logical stuff, and you have the management objects dealing with getting other objects to work together. It's sometimes very hard to mix responsibilities there. This is something that you also find in real life. Like, for example, you have different departments and they sometimes compete for different things in your company. It's just a matter of life that you have to deal with that. And then, of course, you have the data objects. Like, we mostly use namespace objects for these things. And we have task objects for things like, I don't know, batch jobs, for example. Basically, stuff that you need to do, whereas task objects are stuff that you need to do, whereas data objects just store the data in a way that's easily accessible. So how does the internal communication work if you have a design like that? Well, it's actually quite simple. Like I said, you have the system object, which hooks up everything else. So say you get some kind of web request. For example, you want to do an export. So what happens is the system goes to the handler component. The handler component is responsible for dealing with all the incoming requests. It sees that there's a task to be done, so it goes to the task manager. The task manager knows about the various different tasks that can be implemented by the system. It goes to the export task object, and that task object wants to export in, say, XML. So what happens is the export task object goes to the system component, and from the system component it goes to the import-export component, goes to the export manager, and then to the XML export. And that actually implements the XML export. This may look a bit complicated and maybe a bit, I don't know, inefficient, but in the end this kind of system provides the basis for doing loosely coupled components. Because you can easily exchange those components and change everything that happens inside of them. Yeah, for example, the import-export component, when you call it from the export task object that you have, you call a method on the import-export component. You don't call the method directly on the XML export that you have done further below. That makes sense so far? Yeah? Okay. Right. I mentioned you're not supposed to keep state in the component objects. So how do you do that? Well, the best approach that we found is that you simply use context data objects. So you need to work on some kind of request, for example. You put all the data that you need for that request into one single data object. And you pass that data object around. So all the methods that we have in the system, they always take a context parameter. And all the work that's being done is only being done on that context object. So no state gets leaked into the component objects. And that works really well. Right. And again, if things don't look right in your system, then you probably need to do something about it. And refactoring is a very important and very good tool to address that. I have 60 minutes left. I'm probably not going to show you the one part of the slides. I just want to say that when you're refactoring code, it's sometimes necessary that well, I always tell people to be daring when it comes to refactoring, meaning that you should, if you have lots of code to refactor, you should really consider just re-implementing parts of your code and throwing away lots of code, because it sometimes makes it easier for you to refactor. That's something that you should keep in mind. Okay, so let's go back to the example with the company. Just to recap, so structuring a company, you have departments, divisions, you have the layers and the components, you have responsibilities to manage, so you have the management and the data task objects, and you have processes that you define. And the processes are basically defined by the APIs that you have in your application, because each API basically implements a certain process that you have in your system. So what's the conclusion? Well, structured application design can really help you. You can write complex applications rather easily. If you break things up into smaller pieces, it's actually manageable. You can implement very complex systems quite easily. And yeah, complex doesn't have to be complicated. So that's basically the end of the talk. I could now go into some hands-on section. I can do this quickly, or I can turn this into an open space tomorrow. Who wants to do this quickly now, or who wants an open space tomorrow with a little more details? Okay, so we're going to do it quickly now. Who doesn't want to do it anyways? I have 40 minutes left. Oh, okay. Perfect, perfect. Then let's just do this. Right, so of course when you have all your design written up, you know how to structure your application, so now you actually have to code, right? So how do you do that? Well, the slide starts with structuring your modules. I would actually say it's more important to start structuring your file system properly in order to implement those things. The way we do this is we take the layers and have one directory per layer, and then we have under that layer directory we have all the other directories needed for that particular layer. It's very important to put everything into Python modules, obviously. You should avoid, of course, the import star. That is something that can sometimes really create a mess in your modules, especially if you have an import loop. Always use absolute import paths. That's something that I can only recommend. Even though Python 3 now has the relative imports, don't use them. It doesn't look right. Usually don't need them, and yeah, well, it's just from experience. You should always lay out your modules into packages. You probably already do all this. This bullet is in there because the talk is not exactly new. The last time I held it was in 2008 at EuroPython, but it was originally written in 2005. By that time, in 2005, people didn't know packages, so I just mentioned that here. Right, you should basically follow the typical advice that you always get with the Zen of Python. You should keep your modules rather small. You should try to only put one class into one important class into the module. Group things in a logical way. The idea behind all this is that if you have developers working in your project and you get in new developers, you should make sure that they can easily find what they're looking for without having to do a grep over all your source files. So it should be logically structured. You should map your design onto your file system and onto your modules. You should group everything, and well, the natural way of doing that is just using the application and the layer model as basis for that. For the data objects, that's something that's interesting. I know many people like to put data directly into dictionaries, tuples, or lists. What we found is that it makes much more sense to actually write data objects for everything that you do in your application, because it's very much it makes it very much easier to refactor your code afterwards. It makes it very much easier to add new functionality to your data or make changes to your data in a way that doesn't necessarily affect the whole application. Because, for example, if you say you use tuples in your application and you want to add something new to the tuple, then you have to look through all of your application code where that tuple is being used, and you have to change all those different places. And not even the nice tools like PyCharm can help you much with that, because they not necessarily know where all these tuples are used or end up. If you just have a data object, it's very easy to just add something to it. And even Python itself does that a lot. We have we use that kind of approach, for example, for the time struct. When we added new entries to the time. Anyway, I'm not going to go into detail there. We wanted to add something new to something that was a tuple before, and so we just changed the data type to something that was a subclass of tuple, and then we added it to the end, but in an invisible way, so we didn't break code that way. But you still had the functionality. You don't need to go through all this, you just use namespace objects and you're done. The next thing is methods. Methods are very important, even for small tasks. So if you have a large chunk of code there without much structure in it, then you definitely need to break it up into methods. If you have to write more than 100 lines of code in your method, then you're doing something wrong there. You need to break that up into smaller methods. And of course, in the code that you write, you need to group those methods. And that's also how you define the APIs that you do. And it helps in defining the APIs because you can structure your code that way. If you can, you should use mixing classes, because sometimes you have to write certain interfaces over and over and over again, but you need them on different kinds of classes. So Python offers a very nice feature, the mixing class, so you can basically just add that on the side to your class without having to re-implement everything. Very useful and can greatly reduce the code size, and also reduces the maintenance because you only have to make changes for those interfaces in one place. Right, make mistakes and learn from them. Obviously, I mean, you cannot get everything right the first time. And very often the customer also doesn't get things right, and you have to make changes. So if something gets too complex or it becomes ugly for some reason, then you just have to sit down and make a few changes. Sometimes a small change can help you fix that. Sometimes you can regroup things in a different way and it'll work out. But I'd say that in many situations you just have to sit down with the old code and just rewrite it completely from scratch using a better kind of approach, a better design. We're doing that a lot in our work, in our projects. And we always ask the customer to follow this through, because it's a very good investment for the customer later on. If they add new things, new features to the system, having a well-designed application really makes the whole project a lot cheaper for everyone. Right, documentation, very important. I know many developers that love to write code but don't write any documentation to go with it. And with documentation I don't only mean a doc string that says, okay, this, well, you have XYZ method and then you say, okay, this method implements XYZ. That's not really very helpful. The documentation should really be understandable for any new developer looking at the code. It's basically the kind of contract that method has with the outside world. So you should really try to write proper doc strings and really express what the method is supposed to do. Or can skip this one. Oh yeah, no, this one is very important. Use descriptive identifier names. Yeah, even if you have names that are, I don't know, 40, 50 characters long, you have autocompletion in editor, so it doesn't really matter. It does matter when you read the code, because you can immediately see what that method is supposed to do, even if you don't know that method. Right, 6 minutes left. Okay, extreme programming techniques. You probably all know those, right? Anyone who doesn't? Oh, okay. Write unit tests. Well, you hear that a lot. You should do it. Right, typos. Typos is a very ugly bug in Python because they can easily go unnoticed. One way we try to avoid typos in our Python code is that we use the editor's autocompletion feature a lot, because the editor usually knows what we've written in some other part of the project, and it will automatically use the right name of that particular method. So that helps a lot. And other tools that you can use are PyChecker or PyLint or all these other things that you have. PyLint especially is very good for finding typos in application code. You should use that every now and then to check whether you have typos in your code. And obviously if you write proper tests, then you will find out as well. But depending on how many tests you have, it may not actually reach all the different branches in your code. So running one of these tools is a very important thing to do. Okay.
Hello, thanks for the talk. I'd like to know where, if in this model there's also some thought on where to put configuration and how to handle configuration. Does each component have its own configuration management, its own configuration files, or should there be a project encompassing whole configuration? I was just missing the whole concept of configuration here.
Yeah, it's one of the concepts that you have in those components. So you usually have a configuration component that takes care of that. And the way that we do it is we typically just have one configuration file for the whole system, and then it's split into sections. And then, you, for example, you can define for each component, you can define a section in there doing all the configuration there. So we don't have the concept of having for one file per component. There might be cases where you could use that as well, but we found it simpler to just have one.
Thank you for the talk. Yeah, it looks very nice and structured, but then you say use agile, whereas what you're proposing looks to me more like a big design upfront approach. So how do you see it fitting, like, because everybody says, and it's, you probably agree as well with the early release often and all these things, how do you see this very structured kind of upfront design approach fitting with the more agile and kind of early release approach?
That is certainly true, yes. I also like this early release often kind of approach. But if you're, I mean, you can do that for smaller things. If you're doing really large scale stuff and there's lots of money going in and lots of people working on it and you have deadlines to meet, then you really do have to take your time up front to at least get the basic structure of the application right. Because if you get that wrong and you need to make changes in that structure afterwards, then you're not going to meet the deadlines and it's going to cost your customer a lot more. So even though Agile is the right thing to do, you can do Agile on the smaller components in your system, but not on the overall structure of it.
So if I understood you correctly, the components do not carry any data, and they are singleton classes, right? So
Exactly.
one of the questions
well,
I
not
have...
singleton with respect to the system object. So
Yeah, why are you not using modules? That's what they're invented for.
I never store any singletons in modules. I try never to store any kind of anything that can change in a module scope.
Okay, and the system component, the low-level interfaces, you reduplicate them in the system component and forward down to the appropriate component, or you have something like system component dot some subcomponent. Effectively, what kind of abstraction layer is there going on? Is it thin or is it thick for you? Is it a thin layer above the components, or is it doing
the system,
translations?
The system component doesn't have its own methods. It just references the different other components that you have. Say you have a log, say you have a log component. Then what you'd write in all the other parts of the application is you write system.log. and then whatever method you want to use on the log component.
And I have another question. So why do you think it is that the big ones are not using Python if it's more efficient and agile? And so why is Oracle and IBM not doing that?
It's very simple. I mean, they want to make lots of revenue, right? And if you use Java, first of all, you have login. It takes a lot longer to implement the applications. You need many more people in the projects to actually get things done. And I mean, they bill by consulting days, so it makes a lot of sense for them to have the projects run longer than necessary. Well, it's not in their interest to use less time, right? Because they want to make money.
I had seen a question down there. No? Oh, sorry.
this is my experience. Yeah, this is not something that I just make up. I've been in situations where we had to do basically the same thing that a Java group was doing, and the Java group we took something like 2 weeks to do it. The Java group took 6 months, and after 6 months, it wasn't actually doing what they were supposed to do. So, not necessary, right?
Hi. So it was a very nice talk. Thank you. I wanted to ask, how would you approach if you have an already existing large-scale application? If you have an already existing large-scale application that hasn't been really designed at every step of the way, it sort of grew organically. How would you use this approach to gradually move it towards a more structured way, to refactor it gradually?
Right. I would probably start with the very high level layer kind of module, model, and then try to break not break in the sense of breaking the application, but restructure the application in a way that it slowly moves in that direction. So that you identify the different components that you have in your application, you start turning those into those objects, you hook everything together using the system object. That can be done very quickly. It doesn't need much. And very often you have applications that are suitable for that kind of refactoring. And then you start to hook in the old code into your new component objects, so that you get the functionality from the old code, and then you start moving the old code onto those component objects, or you create new management objects to implement the logic. So basically what it's like when you're redoing a building, yeah? You leave the outside in place, but you replace everything inside.
Okay.
After in incremental steps, of course.
Thank you.
Hi. So when you were talking about the steps about making a design more clean, one of them was if you have a class with too many lines of code, that means you're doing something wrong, so you need to refactor and create more methods. Now, when you have certain methods that you know for sure are not going to be used anywhere else, or are not interested from outside of the class point of view, wouldn't that make it a bit more confusing for a developer trying to understand your code if you just create lots of methods that are not interesting for anything else?
I don't understand why you would create methods that are not interesting for others, because when you define the API on the component, you try to only expose those parts that are actually needed by the application in some place. So if you have a very special case that might need a very special method that's only needed in one place in the application, then you're probably doing something wrong there.
Yes, I suppose that's my answer. Like in the API, that's what specifies.
Right. You should probably in that case, you should probably think about having some other more generic methods that you can use to then implement the functionality that you would want in that particular one method that you only need in one place in your application.
Thanks.
Anybody else?
I wanted to comment on the big design up front versus agile topic. First of all, one consideration is we are talking about the 100,000 line of code project, which I expect would mean several hundred classes. So starting out with about 20 of them is not such a big design up front. And the other thing is, one approach that you can try and start with is make a tracer bullet. That is, start with, say, one table in the database, one data object, one interface, one form in your GUI or in your front web part and just connect everything so that everything flows through your architecture, and then when that works, expand on that model and build in iteratively.
Yes. Yeah, you can use that approach. Something that we often do is we write basically markup functions or markup methods, so that you have the basic structure in place, but they don't really do anything for real. But you can still start playing with it. So I don't know, like you say, you just write one path through the application and then just leave out all the rest. Say you have a data component always returns 42, and you can still test your other stuff until you've come to that point and then implemented that particular part of your application.
Anybody else? I have one question actually. So I suppose that most of this software will be deployed into large enterprise customers. So have you ever had the experience of needing to deploy your application on a distribution of Linux it's not your favorite, or in a data center at a customer's premise where there is just some distributions are possible, and how do you cope with that? Have you had problems? How have you solved them?
Yes, we had lots of problems with that, and to the extent that we're not really relying on any Linux distribution Python installation anymore. So we always ship everything ourselves.
Ah, okay, so
basically the whole application also includes Python itself.
Okay.
Plus, of course, all the third-party extensions that we use. We also don't rely on any system provided installations there. Not even the libraries that are being linked to, because we had so many bad experiences with that, and it simply doesn't look good. If you go to a customer, you have the application, you install it, and then you sit there and the sysadmin sits next to you, and then you start it up and you get lots of errors, like link errors or these things, or seg faults, because there's some version mismatch somewhere in a library. You simply don't want that to happen.
You've got a minimal Linux distribution you actually use.
We use, well, basically what we do is we don't really use a particular Linux distribution.
You have yours, so you have all the dependencies you need.
Yeah, we have everything,
Okay.
everything built in, yes.
Oh, there was one more question down there. Okay, sorry, I saw you briefly before.
That's something that might be also interesting for you. Is the developers that we use, they all use their own system. So we have Mac OS X developers, we have ones working on Ubuntu, we have ones working on Debian or OpenSUSE, and that gives us a very nice side effect, because the application becomes very portable that way, because you always detect the different bugs on the various different platforms very early during development.
So what kind of timescale do you put to your designing your system at the beginning of a project?
But that depends on how complex the application is. So sometimes it doesn't really depend on how fast we are capable of working, but it just depends on the timeline we get from the customer, right? So
Is that something you measure in days or months?
it's measured basically in weeks. So for
Okay,
example,
so I
sorry.
think we are.
Yeah.
Time is over. So thank you very much again. Have a nice coffee break, everybody.